Hello and welcome to today's presentation presented by Dlubal Software. Today we'll be working in our structural analysis and design software, RFEM. The topic for today's webinar is tensile membrane structure design in RFEM. My name is Amy Heilig. I'll be your presenter. I'm the CEO of the U.S. office and also a technical support and sales engineer, and we are located in Philadelphia, Pennsylvania. My colleague Andreas Niemeyer will be your moderator, answering any questions you may have. He's a product and customer support engineer located in our Tiefenbach, Germany office. If the control panel does seem to get in your way when you logged into this GoToWebinar, feel free to show or hide that with the orange arrow up at the top. I always want to encourage everyone to ask questions throughout the webinar. You can do so within this same dialog box. If by chance we don't get to all your questions, I will certainly send you a follow-up email afterwards. So regarding the content for the next hour today, and I want to preface that I will end up going over about 10 minutes. So for those of you that have to log off early after that 60-minute mark, that's no problem. We'll always place a recording of the presentation on our website and YouTube channel. So I want to quickly give an overview of the tensile membrane add-on module, RF form finding, and a little bit later on we'll get into the other add-on module, RF cutting pattern. I want to first start off with our example today by importing in a building structure with an IFC file. And the purpose of this is just to make sure that we set up the canopy geometry correctly to frame into our adjacent building. Then we'll move on to modeling, loading, and performing the form finding procedure of these fabric membranes for our canopy. We can even design the supporting structure, which we'll touch on one of our other add-on modules, RF-STEEL AISC. We'll generate the cutting patterns. Again, this will be with the use of the add-on module RF cutting pattern. And lastly, I'll show you how to export these results to both AutoCAD and REVIT. So when we take a look at RF form finding, this module is actually embedded within RFEM. This allows us to perform the form finding procedure of both membrane and cable structures. This process is performed iteratively according to the updated reference strategy by Professor Bletzlinger and Professor Rahm. We can consider both isotropic and orthotropic membranes, which we'll actually see an example of both of those today. We can also consider linear and nonlinear materials. And typically with the form finding process, we might think that we only consider loads such as self-weight, but in reality, we also can consider any free loads during that form finding process as well. Internal pressure could also be considered, and a great example of this might be pneumatic structures where we have some type of internal gas chamber that we need to consider for the form finding procedure. And lastly, we can consider the interaction with the supporting structure. So point being, we can design the entire form finding membranes, the cables, and the supporting structure all within one program, RFEM. So I want to jump into our example today, and we will start off with a new file within RFEM. So you can see here I've given it a model name. We are in a 3D type environment, and we can generate the load combinations automatically according to the ASCE 7. You'll see here the NBC standard, many other international standards. So that will be taken into consideration when this checkbox is checked. If we uncheck this, then we can manually create those load combinations instead, and this drop-down box will be ignored. Under the Options tab, this is where we activate the Form Finding module and the Cutting Pattern module. I also want to enable this third option down here, Enable CAD BIM Model. So when I click OK, we are brought into our main program, RFEM. And I like to just give a quick brief overview for those of us who have never used our program before. We have our graphical interface here, so as we begin to generate that model, we'll see that right here in our center window. We have our tables to work with down at the bottom. If perhaps we like to work in a table format with our input data, we can do so here. Our loading, our load combinations, our results will also be available within these tables. Up at the top, we have our quick tools, which we'll certainly be utilizing quite a bit today. And over on the left, we have what's called our Project Navigator, which I like to say is a little bit more unique to our program. So as we begin to generate this model graphically here, we'll see all of our input data available over on the left. This will allow us to make quick changes to materials, to cross sections, even loading, and so on. We also have all of our load or our modules listed here within the project navigator. So you can see this long list of add-on modules. Now you won't find form finding or cutting pattern within this list here. That's because we just activated it within that general data tab. But with RF-STEEL AISC, which we'll touch on later, that's an add-on module you can launch from here. Now, our results will also be available to us within the project navigator, which we'll get into a little bit later on. The fourth tab down here may be new to some of us. So by enabling that CAD BIM model option, we now have this fourth tab to import in an IFC or a step file. So I can just simply click on one of these buttons and I have available to me my IFC building for my office building. So with a few steps, we can see here that the IFC file is imported into our main program, RFEM. Now, I want to be clear that these are still just components. They're not actual elements within RFEM, meaning they're not surfaces, members, they're not solids. We would need to convert those to elements in RFEM. So right now, this is just serving as architectural purposes. And in particular today for this concrete office building, I'm trying to design a canopy on the front face of this building, but I want to make sure that it lines up perfectly with my front face of this office building. So that's the whole purpose of importing in this IFC file. We're not going to be designing the building today. So what I can do is to take one of these elements, and in particular, we'll start here with our front slab. I can right-click to create a surface. Now, the program generates some arbitrary thickness and selects some material within the model. This really doesn't matter. We're actually going to end up deleting this slab. We're purely using the nodes and lines for geometric purposes to generate our canopy structure. So I can just click OK. So once I've done this, I can actually hide my IFC file, and all I'm left with is this shell element that I converted from that file into RFEM. So what we'll do here is to turn this into wireframe view with my view options up at the top. And I'll take this line element on the left side of my slab. I'll right-click to divide the line by a certain distance. So here is where I can select 23 feet from the line end, and I can see with my black arrow here what's the line start and what's the line end. I click OK. So all I've done is generated an additional node here right along this line length. Now I can hold down my control key and to select that new node in addition to this node here. I continue to hold down my control key and I take advantage of what's called our drag and drop. This allows me to make quick copies within the model without using that move copy tool. I want to additionally use this connect lines or members tool up here at the top. So I select this, and what this allows me to do is to highlight over that node, and it simply broke that line apart in two. So I take these newly generated nodes, holding down my control key to select them, and now I'm going to use my move copy tool. I'm going to create one copy in the global Y direction, which I can see my global coordinates here of -30 feet, and I click OK. So here are these new nodes generated in a distance of 30 feet in the global Y direction. Now I need to add in a node right here at my origin. So there's several different ways to do that. Up here in our quick tools, we have the option to draw a new node, which I could just easily snap to the drawing grid here at the origin. We also have this feature that's called node between 2 points. So when I select this option, I can click on the node on the left, the node on the right, and the program automatically suggests that I'd like to place a node right at the midpoint. I click OK, and I know it's a little bit difficult to see because of those axes there, but a new node is generated right at the origin. So when I select that node, I can use my move copy tool again to create one copy, this time at a distance of -33 feet in the Y direction, and I click OK. So this node here will highlight, use our move copy tool, and move it now a distance 26 feet in the global X direction. Once I've done this, I can hold down my control key to select both of these nodes and again use that drag and drop feature to make a copy of the node on the left side. So now that we are done with the basic nodes at the bottom of our canopy structure, I'm actually done with this surface. So this is where I can just select it and hit delete on my keyboard, and we can clean up the model by deleting all of these various line elements that we don't need any longer. So I'm just simply clicking on them, hitting delete on the keyboard, and just like that, we're left with only our nodes at the bottom here. The next thing to do is to generate our columns. And these won't be columns yet, they'll just be lines, such placeholders, which we'll later assign a cross-section and material to. In order to do this, I want to select the nodes that I'm first interested in. And you can see I'm holding down my control key to select various nodes here. I use my Move Copy tool. We create one copy in the global Z direction. So this is the vertical direction of 23 feet. Now, before I hit OK, I'm going to go into this Edit Expanded Settings. What this allows me to do is to create lines between my copied nodes. So essentially, this is just saving us an extra step rather than having to draw those lines manually. So you'll notice once I click OK, then those line elements that will eventually be our columns are drawn here. Now, in the rear of my canopy, this is actually where it will be framing in directly to the office front face. So I don't need to draw columns back here. Rather, we're going to attach at the top of the canopy directly to the office building. So what I can do is to highlight these line elements and my bottom node and delete them all together, and I'm just left with these nodes up top. Now, in a similar fashion, I want to select the individual nodes that are left down here at the bottom, use my Move Copy tool once again, this time only a distance of 16 feet. We leave this setting here to create lines between nodes. I click OK, and here are my additional columns. Now again, back here, we're framing directly into the office building, so I don't need these columns back here, but rather just these nodal points at the top. And just like that, we have finished with the basic geometry here from that initial slab. So I'm going to turn off my grid down here at the bottom, and I'm only left with these node points, and I'd like to draw the outer profile of my canopy structure. I can choose a new line element here in our quick tools. And keep in mind, I still have drawn no members within the program. These are just simple line and nodes. This is exactly what you would think of as an AutoCAD, just line elements only. And we choose this straight line option. So here is where I can snap to these different nodes that I've generated. And the program's fairly good about using the O-snap settings to snap to the top of these nodes. So I continue around drawing the structure as such. We right-click to exit, and we have the outer profile shown. Now, I do need to draw lines to define the individual cells here of my canopy. So I can continue doing so by just snapping from one node point to another. And we do so on the right side of the structure. And just like that, we are finished. So if we're interested to see how these elements frame into my office building, I can always reactivate this IFC file of my office building. So remember, these are just components that are used for architectural purposes. So I want to make sure that my canopy isn't framing over any windows or doors. And so far, it looks okay. So we turn that IFC file back off, and now we want to begin drawing our cable elements. So our cable elements are going to be placed on the boundary lines of my fabric membrane. So this is pretty common within membrane construction. These tensile cables will take the tension forces as the fabric is stressed. So at locations here where we're framing directly into the office building, these line elements that I'm hovering over will be cable elements. So we can just go ahead and assign cross-section properties for the cable elements to these lines directly. But for the other line elements up here at the front of the structure, we have a small issue. These will eventually be HSS steel members, but I also want to show cable elements at this exact same location. Well, the problem is that both the steel member and the cable elements cannot share the same line. So I actually need to draw a small offset line here to represent my cable as an arc member. Well, how I can do this is to turn back on my grid down at the bottom, and we don't want to use these global X, Y, and Z coordinates because we have some pretty odd geometries here. Well, we have a nice feature in the program up here in the top where we can actually define our own work plane by clicking on 3 grid points. So how I can do this is to click this option once. I click 3 times to define my grid, and then you'll notice that my drawing grid is automatically placed at the incline that I've specified with those 3 points. So it has a new coordinate axes of U, V, and W. So with this new coordinate system, I'm going to go up and draw a new line again, but this time I'm going to draw an arc via 3 nodes. So what I can do is to simply click on the point closest to what will be my office building, and to click on the column point, and there we have it. We just have a simple arc element. Now keep in mind, the arc radius is completely arbitrary. It doesn't matter what we set this to. The program will later on override this shape with the form finding process based on the pre-stresses that we put in to find the correct catenary shape for us. So I'm going to do the same thing at a different location here for my cell points. Again, completely arbitrary. We need to move up to the second cell, and we need to change our user-defined drawing grid. So I click first to reset the drawing grid, click it again to define my new point, and I can click on 3 points here. And now you'll notice that I have a new drawing grid at a specified angle. So we go to draw a new angle here with the given arc, and I can simply snap to these points, again, any arbitrary points. We need to lastly do so over here. So we click this option up in our toolbar for a user-defined grid, click our 3 new points, and now we have the specified angle is given. We go back to draw a new line element as an arc with 3 lines and continue on with this process for our additional cable elements. And one more time for our 3rd cell. So deactivating this grid down here at the bottom, I have these cable elements shown here, and I'd like to show them on the other side. So rather than going through that entire process again with our user-defined grid, we can hold down our control key to select what will be these cable element lines and take advantage of our mirroring tool. Mirroring tool, exactly like what it sounds like, similar to what you'd see in AutoCAD. We can create a copy by mirroring about the global YZ plane, and I can click any point within the model to mirror about. I click OK, and here we are presented with our what will be cable elements on the other side of the structure. So that just saves us an immense amount of time. So now that we've defined the boundary lines of what will be our fabric membranes, we can move on to drawing those 2D surfaces within the program. So for this, I would typically suggest for a flat membrane to draw a new surface element. But you'll see here all of these surface elements within RFEM are only considered in a single plane. Well, if we take a look at this very complex geometry, I think we can make the assumption that these surfaces are certainly not in one plane. So this is where we need to use the option for a quadrangle instead. We can use that from our drop-down list here, quadrangle, general 4-sided surface. The stiffness will be set to membrane orthotropic. And the next thing we want to do is to define here what will be our membrane material. So in all cases for these membranes, you're likely going to have to create a new material. So we can do so by creating a new material, which our dialog box pops up. We can give it a name. We'll call this one membrane. We even can change the color. So perhaps for my model here, I go into my color palette and I'd like to use a green color instead of blue for my fabric membranes. We change the material model here to orthotropic elastic 2D. Now, I want to preface this that with this information here, this is likely you're going to get from the manufacturer. Maybe you have your own testing methods or whatever relevant resources you have. For our example today, we know from our manufacturer that our fabric membrane is stronger in one direction than it is the other. But this is actually something that I'm going to set in as an isotropic membrane for the time being. The reason why is because I don't know with these complex shapes of my membranes, complex geometry of the canopy, which way I should span that strong axis of my membrane to take the high tension forces. So I'll show you later on how we can easily determine that. So for right now, we want to set this to an isotropic material, which means it has the same stiffness or the modulus of elasticity in both the X and Y direction. But keep in mind, we'll come back in later on to adjust this. Now, as far as the shear modulus in the first two directions, we have relatively no shear strength, but in the plane of the membrane, in the XY direction, we want to set this to 7.25 KSI. Poisson's ratio, we can set this as 0.3, and I click OK. The specific weight, again, probably comes from the manufacturer. We will set this to 32 pounds per cubic foot, and the rest of our information we can leave as such. So now we click OK, and we want to go into this option here, Edit Parameters of Surface Type. Well, the first thing we want to set here is our thickness of our membrane under our second tab. So we'll give this a thickness of 0.04 inches. What's quite powerful is that we can view the stiffness matrix of our membrane. So if you're interested based on the material properties that we put in here, this is exactly the stiffness matrix that will be reflected in the RFEM model. And finally, our form finding tab. This is available because we have activated the form finding module at the beginning of the presentation. We have two different calculation methods for this, either standard or projection. So standard is pretty typical for fairly flat membranes, and we'll be using that for today. Projection would be used for more conical type structures. So with the standard calculation method, we can specify a pre-stress force in both the warp and weft directions. This is in the X and Y directions, and we'll choose 0.5 kips per feet. And I click OK. So now we're done defining all of the various settings for our membrane. We click OK. The program's asking me to go ahead and define the boundary elements of my fabric membrane. So you can see that as I begin to click what will eventually be these cable members, that our fabric membrane is created. And lastly, our last cell over on the right, we right-click to exit out of that dialog box. Again, if we're curious to see how this frames into our concrete building, we can activate that IFC file, and we can see that everything looks to be great so far. So deactivating that, we want to move on to the cable elements. So again, right now, all of these cable elements are just lines. They don't have a cross-section or material defined. So what we can do is to hold down our control key, select all of our membranes, and I'm going to choose a visibility by selected objects. When I do this, I can highlight all elements within my model. Now you'll notice that down here, my column lines and the other various lines are not available to select. That's because I've deactivated them in my view. I only can select my membranes and their boundary lines. So I can right-click to edit the lines. And we're brought into our line dialog box. And the third tab here is called Member. This is where we can make a member available by selecting this checkbox. And here is where we can set the member type to cable. The program's telling me I need to create a new cross-section, so I'll access my cross-section database, which you can see here we have all of our various cross-sections available within RFEM. We have several parametric sections, massive sections, thin-walled sections. We have all the rolled sections from the various standards, and in particular today, I'm going to use this solid sections. So this just has some pre-populated diameter. They're basically just round bars populated from the AISC with set diameters, but you can always create your own with a parametric section. We'll choose a 1/2 inch diameter cable. The material is also set within this same dialog box. So with the cable materials, I'm going to access my material library. Similar to the cross sections, I want to use my filters over here on the left, and I choose metal, but under my second drop down, we can choose cable. Now, typically when you first populate this, you'll only see a few materials available here from the manufacturer Pfeiffer. If by chance you're using this manufacturer, then great. Your materials are already set within our database, but likely you're probably going to have to add your own from whatever manufacturer you're using of those particular cable elements. So we can do so adding our own material with this button down here, Create New Material. So what I went ahead and did is I created a new material, which if I back out of this, we'll be able to see it. And I called this one my ASTM cable material. Then we can put in the material properties, and you can set the applicable filters over on the left that you would like them to be available. Once you have input in these material properties and you've saved this material description, it will always be available for any future RFEM model. So you don't have to define it every time you create a new model. So once we've done this, we'll go ahead and use this ASTM cable material with my material properties shown here. I click OK. And before we click OK out of this dialog box, similar to the membrane elements, we need to set our form finding settings. So I go ahead and click on this expanded settings dialog box, and this is where we can activate either a target cable length, a cable sag, or maybe we just apply a pre-stress force directly. So this is only available with RF form finding activated. Essentially what this allows us to do is to model these cable elements as either straight lines, which you can see back in my RFEM model, or pretty much any arc shape like this. And everything will be overwritten based on these settings here. So for today, I want to use a target cable sag of 10%. I click OK. I click OK through all of these dialog boxes. And now, I know it's a little bit difficult to see, but we do have cable elements set for the boundaries of our fabric membranes. So I cancel out of this visibility mode, and we need to continue with this same manner for the additional line elements that are left here. So we'll start off with our columns. So I'm just going to use my selection box here to highlight over the vertical lines only. I can double click, and again, we have a member tab where we can make this member available. Now, of course, we want to change this member type to beam. We certainly don't want cable elements for our columns. We want to choose a new cross-section from our cross-section library. And here is where we can access our HSS sections directly from the AISC. So within this drop-down box, you'll also see the various other standards and manufacturers available. In particular, the CSA standard will be available here as well. So we choose the AISC 15, which is the latest version. Now for my canopy structure, I'm really not trying to detract too much from the aesthetic appeal of this office building. And we know that this canopy isn't going to take a high amount of vertical gravity loads. So what we can do is to choose a pretty low profile section here. We'll choose an HSS 4-inch diameter here, which we can see the cross-section properties available to us with this info button. The material is also set within the same dialog box, similar to what we just saw with our cable elements. So we can access our material library, and we use our filters over on the left here to select steel from the ASTM, and here we have available the 2016 version with all of the AISC materials available to us here. Again, if you want to create your own material, you can do so with that same button down at the bottom. For today, we want to choose A500 grade B, and our given material properties are shown here, and I click OK. So once I'm done with these dialog boxes, you can now see these columns have been generated with the applicable material and cross-section shown here in the rendered view. So we need to continue doing so for our remaining line elements here. These will actually be our compression members, which we also want to set as HSS. And we'll double click on these lines. Again, we're just choosing the member type available here. The member type this time will be set to truss. The only difference between a truss and a beam member is that the program's automatically going to release that moment at the member end. So it's just a quick way to set in the program that we want to transfer only shear and axial forces. You'll notice that my member hinge option is grayed out down here. We go to our cross-section library once again. We choose our HSS sections, and because these are taking quite a bit higher loads, especially in compression, we need to choose a bigger diameter. And in particular, we'll choose 7.5-inch diameter. I've already defined that steel A500 grade B material, so I don't need to define it again unless I want a different material category, but it's available to me here within my drop-down box. So I click OK. I click OK once again, and now you can see those HSS members available for our structure. So before we can run the form finding procedure, we obviously need to support this structure. So what we can do is to select a new nodal support up here in our toolbar. I choose a new nodal support, and we have a few default options shown. I will use the first default option, but to explain what's going on with these nodal supports, we have our 3 degrees in translation and our 3 degrees in rotation. So for the bottom of my columns, I'm going to restrain translation. I also want to restrain rotation about the global Z direction. This is purely torsion for that column, so it's not free to rotate about its own axis. We also have the partial fixity here for spring supports, and the nonlinearities are important, especially for today's presentation, because we have an option here called the form finding stage only. If by chance you want to apply a nodal or line support during the form finding process when we're applying these pre-stress forces to both our membrane and cable elements, and you only want that support to be applied during that particular stage only, we can select this form finding stage only. You'll notice the nodal support changes to blue to indicate there is a nonlinearity. So what will happen here is it will only be applied for RF form finding to find the initial pre-stress shape. Then for all other subsequent static loading, such as live load, dead load, snow load, and so on, the support will not be considered at all. So extremely helpful for when we're trying to find stability during that form finding process, but you do in fact want to make sure that this would truly be available out in the field when you are pre-stressing these membranes. You don't want to use them in the model if you're truly not using them out in the field. So for today, we're just going to use that first hinged option for our support with no nonlinearities applied, and we apply them to the bottom of our columns. Now, for the locations framing into the office building directly, we also want a pin support, which I can access my nodal support once again. I'm going to create my own definition here because I want to release the moment in the Z direction as well. So I only have a typical pin with translation restraint in the X, Y, and Z. I've now defined that particular support type, so I can click directly on my nodes where they will be framing into the office building. And just like that, we are done with our geometry. So back under the data tab, as I mentioned, all of our input data has been applied here, so we can easily make changes to all of these cross sections as well as materials. The next thing to do is to run the form finding process. So I have applied no loads to my structure yet. I've only applied those pre-stress forces. In my drop-down box here, we see RF form finding available to us, and we can easily run a quick analysis for this. So all I'm doing is applying those pre-stress forces to both the membrane elements and the cable elements to find the true deflected shape here after those pre-stress forces have been applied. So what I'm presented with are my results within my project navigator. So we can see that tab available to us here. What's probably most interesting is the initial deflected shape. I think that this is very telling for us to know if we've defined everything correctly. If you're seeing a deflected shape that makes absolutely no sense to you at all, then you probably have modeled something incorrectly. Perhaps we're missing those cable boundary elements to take those high tensile loads. Maybe you're running the wrong calculation method with the form finding procedure. So you definitely want to take a look at the deflected shape here. So what the program has done is it has created a new deformed mesh based on my settings here that we can now move forward with. But before I do so with the additional loading, I want to point out some very powerful features in our results that are given to us after running RF form finding. So the first would be to take a look, of course, at our global deformations, but we can also look at our surfaces, and in particular, the NX and NY forces. So these are the tensile forces that have been applied to our structure. And remember, I set this at 0.5 kips per foot, and that's reflected here almost identically within my basic internal forces, NX and NY. So that's a really good sign that the pre-stress forces are available to me with these axial forces for my membranes. The other interesting thing that we have within our results is under the shape tree. We can view the different contour lines. So the contour lines are going to show us from the origin point of 0 exactly what elevation we're sitting at here in terms of inches. So obviously the points that are sitting up at these higher columns are going to have a higher contour line than at the membranes that are sitting at these lower columns. We can also view the inclination. So this makes perfect sense that if we look at this location here with red, we have a pretty steep incline where this fabric membrane is framing into that support. But at these locations at the center of the membrane, we have almost no inclination of 0. That's where the fabric remains fairly flat. We can also view the inclination direction here just to give us a sense of exactly how this fabric is pre-stressed during that form finding procedure. So in addition to my surfaces, I also have the internal forces available to me for my members. So perhaps I'm interested in viewing the axial forces within some of these HSS members. So I can take any one of these members and maybe I create a user-defined visibility here. I'm only looking at this single HSS member and I can view those compression forces based on the pre-stresses that were applied to the membranes. Now I can always right-click to view the results diagram. What's nice about this is I can view in a little bit more detail exactly what's going on along the member length here. In a similar sense, if I cancel out this visibility and I'd like to take a look at only my cable elements, well, under the Views tab within our Project Navigator, we actually can select our members by type and choose the cable elements only. So now I'm only viewing the results for my cable elements. I go back to my Results tab and I can view the axial tension forces within these cables. In addition, we have a couple options available here under member length. We can view the stressed length of these cables as a member diagram in terms of feet. So this is the length after we've applied that pre-stress force. We also give to you the unstressed length. I think that this is really important because this is information we want to give to our manufacturer to ensure that they manufacture these cables at the correct length, which would probably be this unstressed length, so that by the time we get out in the field and we apply these pre-stresses, then we should achieve this stress length here. So both are given to us. Now, additionally, if I take a look at the full model view here, we also can view the support reactions. This might be important here for designing the connections that are framing into our office building. All of that information is available for the form finding process only so far. So of course, much else to cover, but we'll go ahead and move on with our structure. So I have only applied those pre-stress forces. I've applied no additional loads to my structure, such as live load, snow load, and so on. So we want to go ahead and do that now. I'm going to create a new load case up here in my toolbar. And up pops my edit load cases and combinations. So my first load case description will be self-weight. What I'm going to do here is I'm not going to put self-weight under dead, but I'm actually going to put it under form finding. So what exactly am I doing here? Well, that form finding process that I just showed you did not include self-weight. So just keep that in mind. Now, in reality, when we go out to the field and we pre-stress these elements, it's inevitable that self-weight will, of course, be included. So likely you're going to want to come in here, create a load case under the form finding category with the self-weight active in the negative Z direction here to account for that during that RF form finding process. We didn't do that, but now we can account for that with this load case. Now, any other loads that are available, again, pneumatic structures, we'd want to put them under this form finding case. Now, it's important to understand that for any additional load cases, and you can see here the program's telling me I have to clear my results because the previous results are no longer valid, we don't want to add any additional self-weight to any of my other load cases. We've already accounted for that in that initial self-weight load case here during form finding. My second load case will be live load with the action category set to live, self-weight is unchecked. I create my third load case. This will be snow with the action category set to snow. My fourth will be wind in the X direction with a downward pressure. We'll set the action category to wind, and we can easily make a quick copy of that to set wind in the X with uplift instead. So I've defined all my different load cases. Now, especially with wind, you'll probably have many more load cases to consider. But for example, today we'll just set a few. Under the Actions tab, this is more so important not for load cases where we've only defined a single load case such as live load, snow load, but wind load. We have two different load cases for this particular action category. So this is where you tell the program, do you want it to act alternatively, simultaneously, or differently? Well, we don't want our two wind loads acting at the same time, so I've set this to alternatively here. My combination expressions, the program will generate both LRFD and ASD load combinations. Remember at the beginning of the presentation, I've set this to generate automatically according to the ASCE 7 2016. If I'm not interested in ASD load combinations, let's say we're not really designing for deflection today, and when I get to the steel AISC module, I'm going to design per LRFD. So I can simply deactivate those here with this use checkbox, and I can also delete them if I prefer to. But I like to use this option in case I want to come back and reactivate them. My load combinations tab will then simply list out all of my LRFD load combinations here based on the standard. My result combination is just simply an envelope solution for both my max and mins will eventually be presented to us within our results for all of the LRFD load combinations. So what I've done now is I've set up those load cases and combinations, which should be available to us in our drop-down box here. But now I actually need to apply those loads to my structure. So my self-weight load case, we don't need to do anything. Everything's done automatically there. My live load case, well, according to the ASCE 7 2016, and in particular Table 4.3-1, this addresses awnings and canopies for fabric construction. And what this requires is a minimum live load of 5 PSF. So if we adhere to that, we want to apply a new surface load, which we can do so in our quick tools up at the top. The load direction will be set in the global Z direction with a magnitude of negative 0.005 kips per square feet. I click OK, and then I just simply highlight over all of my membrane surfaces. In a similar fashion, we want to apply snow load. So what I'm going to do here is go back to a new surface load. You'll notice I have snow load selected in my drop-down box here. And now my load direction is going to be in the global Z projected area. I'm going to apply a fairly small magnitude here. Let's say we're in an area that we're not too concerned with snow loads, but we want to apply 6 pounds per square foot. So when I click OK and I highlight over all of these members again, the advantage of a projected load is it will take into consideration those inclinations of my surfaces. So areas where we have high inclinations, that's where we're probably going to see the snow slide off essentially. The program will account for those angles, but at these areas where our membranes are relatively flat, we're going to see higher snow loads there. So that's the advantage of a projected load. When it comes to our wind loads, according to the ASCE 7, Table 30.11-1, this does address wind loads on attached canopies. So for time's sake, we don't have time to get into this today, but I just want to briefly mention that. For these specialty type structures, I want to mention something back in my PowerPoint we are currently working on in development. And this is going to be a standalone program called RFlow. Well, what RFlow will eventually allow us to do is to simulate wind flow around structures. So what this will help us do is to understand wind effects on specialty structures where there's really no clear approach within the various standards. So it could be argued that our particular canopy today is a pretty complex geometry. You know, it's framing into this office building. How exactly do these wind loads affect these specialty structures like this? So this will be a huge advantage once eventually we do release that. It's not quite ready, and we do plan to integrate it with the RFEM model. So you'll be able to bring in the geometry into RFlow, apply these wind loads, and in turn we'll be able to export those wind loads back into the RFEM model to be considered in the analysis. So I did want to mention that, something exciting to look forward to, but for now, we have to jump back to RFEM and manually apply these loads. So for our simple load cases today, we will apply a new surface load here in the projected X direction. So I only want the surfaces that have actual face value according to the global X-axis to be affected by these wind loads, and we give it a magnitude of 0.15 kips per square foot, and I can highlight over my particular membranes here. Now for the downward pressure, we go to a new surface load and we want to apply this according to the local z-axes of my membrane. And I'll show you in just a minute how we can view those local axes, but just trust me that the z-axis is how we want to apply those to our structure, and we will give it a magnitude of 0.02. So this is going to be based on the local axes of the member, so now we can see those loads applied no matter what the geometry is normal to the surface. For our wind in the X uplift direction, exact same scenario here. We just simply want to change the magnitude direction and put a negative here for our uplift pressure, highlight over our members, and now you can see that uplift pressure normal to all of those surfaces. We also want to apply that small lateral load in the X projected direction. This time we'll give it a slightly higher magnitude than the previous load case, and we highlight over all of our members. So then we can just scroll through here to take a look at all of the different loads applied to our structure based on wind, live, snow, and of course self-weight is in there too. Before we're ready to run an analysis, you'll remember several minutes ago that I explained that we're setting this to an isotropic material. In reality, we have an orthotropic material. I need to determine which way to orient these membranes in order to take the highest tensile forces. So how exactly do I consider that? Well, what I want to do here is to jump to only my live load case, and I'm going to go ahead and apply the live load case only to the structure. Now remember, we lost our form finding results previously because I said, well, I want to include self-weight now. So we're now including self-weight. The program needs to run back through that form finding procedure. Then we're applying the downward load for live load. Now, eventually the program is going to cycle through. You can see the iterations here for max displacement for the different iterations applied, and eventually we'll be presented with our results. So again, we're using just this single load case here to determine where these high tensile forces will be acting on our structure. So now we're presented with our results here. So this is similar to what we've seen before, of course, but now we have this live load acting down on the structure. I'm going to right-click on these surfaces to view my local axes. So there's my X, Y, and Z axes. Now, if I take this into an elevation view, I want to choose this option surfaces here from my results, which we've already been in before, and in particular alpha M. Alpha M is going to show me my trajectories for my load distribution, in particular for N1 and N2. So this is showing me where my high tensile forces are within the member, and we can use it in addition to this colored profile panel here. Well, if I take a look and I compare, I know it's a little bit difficult for you guys to see, I can see that my high tensile forces are spanning, looks like closer to the office building here support down to where this column is for my first membrane. If we take a look at the second membrane, we're going to see the higher tensile forces spanning in the opposite direction here from our upper left column down to our lower right, and so on. So how do we orient our local axes of these members to make sure that they're taking the high tensile forces? How we do this is I'm going to turn back on my grid down at the bottom, and I'm going to uncheck the option for my user to find grid, and we change this in the XY plane. So now we're just looking at that drawing grid at the bottom of our structure. We probably want to take a screenshot here, or maybe we can just approximately remember which way these high tensile forces are spanning, because once we draw a new line element here, which is what I'm about to do, the program's going to suggest that I have to clear my results in order to change any type of the geometry within the model. That's not a problem. I'll go ahead and create my first line element spanning in those high force areas. I clear my results, that's fine. We right click, we do the same thing here for our second membrane, and finally our third membrane here. I'm going to take these two line elements on the left side and I'm going to mirror them about my YZ plane. I click OK, and now I have those line elements shown on the other side. So you might be thinking, well, what in the world are these lines going to help us with down here? If I go back to the elevation view and I double click on my first surface here, I have an axes tab. This axes tab allows me to line up the local x-axis parallel to any line that I choose within the model. And I choose that line element I just generated. I click OK. So now you can see the local x-axis lines up perfectly with that line I just generated. We haven't really affected our model otherwise with these line elements down at the bottom of the structure. I do the exact same thing here for my second axis. So I choose the axes tab. I select my x-axis parallel to my line here, and you can actually see it's fairly close already, and it lines it up to my second line. Same option for my third membrane. I choose the local x-axis parallel to line number 38. We continue doing so around the remaining structure. What's nice is that the program automatically populates that tab that I was just in, so I don't have to fumble through trying to find the same axes tab each time. And lastly, we choose our last fabric membrane, line the local x-axis to line number 39. I click OK. So you can see that now the local axes are all lined up to take those high tensile loads. The final thing we need to do before running our analysis is remember my materials, which I can access here from my project navigator. I can either select it graphically as well, but an easy way is to highlight it here in my project navigator, the membranes that utilize that material highlighted. Concurrently, I double click on it. I go back into my material model settings here, and now this is where I change the stiffness in the weaker direction of my membrane, EY, to 44 KSI, and I click OK. So this is just an easy way to determine here exactly which way your fabric membrane should span in order to take those higher forces. So once we have done that, we're now ready to run our analysis for all these load cases and combinations. Now it does take just a minute, so for the sake of time, I went ahead and have run all those load cases and combinations, and we should be presented our results available to us here within the project navigator. And I can scroll through the different load cases and combinations, and in particular, I'm looking at the deflection. What might be interesting are these uplift load cases where we have that wind pressure applied. So of course, all of those same results that I just showed you are available here within the project navigator, which we don't need to necessarily go through all of those again. What I do want to briefly touch on is design of the supporting structure. Or actually, let me back up one more time. I want to also explain, though, that when we are designing these fabric membranes, we want to take a look lightly at NX and NY. Now, probably from the manufacturer, we're given some strength for this material. We want to make sure that we're designing with a specific safety factor in mind. Now, this is usually around 5 or so of the material strength, so you can compare that to these basic internal forces. Now, this all depends on which project you're designing for, maybe which state, which standard, and so on. So that's really up to you as the engineer to determine, but that's likely the information you're interested in for the fabric membranes. Now, as far as our steel members, this is where I want to launch our add-on module RF-STEEL AISC. Now, we also have RF-STEEL CSA for Canadian steel design. And this module is a little bit different than, of course, what we saw with form finding, which was embedded directly within RFEM. This brings up a dialog box here. And all of my information is brought into this add-on module. I'm just defining a little bit more information that's specific to the AISC standard for the design. Now, I want to explain that I'm really going to breeze through this quickly. I've done previous webinars devoted entirely to steel design that I'd like to refer you to on our YouTube channel if you are interested for more information on this. The whole purpose is just to explain that you can do the entire structure design all within one program. So for this, we want to select our members to design. And an easy way to do this is to jump to my Views tab within my Project Navigator, and I can select my members by material. And I'll choose my Steel A500, which includes all my HSS members, and I can graphically select them here. I can choose my LRFD load combinations to design per the ultimate limit state, and I'm designing per the AISC 2016 LRFD. Now you can see that the materials are populated here. Steel A500s brought in. My cross sections are all brought in from my main model. The effective lengths, for example, would be my unbraced length for buckling about the strong and weak axis, flexural torsional buckling, lateral torsional buckling, and so on. So what we can do is run a calculation here. Now, all those internal forces for my members from all the different load combinations are quickly brought in. You can see how quick that solves. The AISC equations are applied to each member, and we can view our results in table format. So when we view the design by member, we can scroll through all of these different tables here to see how exactly the AISC has played out for these particular members. You'll notice everything is highlighted for these tables and synced up within the RFEM background. We're getting a design here for our HSS members of 0.83, which I would say is pretty great for design purposes. We can view this information graphically back in RFEM, so we're technically still within this steel AISC module, but we're viewing our results graphically here back in RFEM. So again, I know a really quick explanation, but again, refer to those previous webinars that I have created. Okay, so the next thing that we want to do is to quickly generate our cutting patterns. And for this, what I'm going to do is to go back here to my PowerPoint to explain a few features of the add-on module RF cutting pattern. So what this allows us to do is to generate small planar cutting patterns in a 2D environment where we will eventually be using them to create a double curved membrane in a 3D environment with those pre-stress forces applied. So an easy example of this, and of course this reflects our model today, is that if our end structure, we'd like it to look like this, well, we obviously need to give some information to the manufacturer that's creating these fabric membranes in a 2D environment so that when we're out in the field, these will fit together quite nicely. So it's actually a very complex behavior to generate these 2D cutting patterns. And RFEM in particular uses the minimum energy method. So this is a very accurate analysis. Now this is in comparison to a lot of other cutting pattern programs that are out there that are typically using some type of geometric flattening method. The minimum energy method is much more accurate and efficient for complex geometries. What the program will do is it will press the mesh geometry of the curved surfaces into a plane using a press with frictionless press areas. This eventually results in our tension and compression stresses from this flattening process will be in complete equilibrium. So the huge advantage here of utilizing this minimum energy method. Now, in addition, we also can take into account uniform or linear compensation in the warp and weft directions. Compensation is simply the amount that we need to deliberately shrink these panels to account for the elastic stretch of both the membranes and cables, as well as for the creep of the membrane. So over time, that membrane is going to continue to stretch out. We can account for different allowances as well, and this is simply just additional fabric to attach to the membrane, or to use for the membrane to attach to boundary lines. Maybe that's our steel members, or for overlaps to weld these panels together at these seam lines. And finally, we can output all of this information of the cutting patterns graphically, whether that's in RFEM in our printout report, in tables, which we could export to Microsoft Excel, as well as DXF files, which I'll show you today. So jumping back to our RFEM model here, we want to begin by generating our cutting patterns. So I'm going to exit out of the results view here, and I'm going to create a new user-defined grid. This is exactly what we saw before. I'm going to select this option here and click on 3 different points, and you can see that the program automatically places that grid right through the center of that membrane. To begin generating my cutting patterns, I right-click on a line and I choose a new line, Cut via Section. Here I can select only my first surface. I click OK. Then I choose my first point of my cut, which will select at this point closest to our office building, and my second point will be where it frames into this lower column. The cut type will be geodesic with a definition of a direction vector here in the 001 orientation. So when I click OK, the program automatically creates this line element here right through the membrane element with the form finding shape considered. So what I need to do is, this is still too large of cutting patterns. I still need to continue drawing these geodesic lines further on this particular surface. So I take this element, this line element, and I now use my Move Copy tool. Instead of using the global X, Y, and Z axes, I'm going to use that user-defined axes that I just created in the UVW direction. And we're going to create 2 copies here in the V direction of 6 feet, and I click OK. So now you can see the program has generated a couple other line elements here. We use the Move Copy tool once again in the V direction, only 1 copy with a spacing of -6 feet, and I click OK. So what we want to continue doing is placing these geodesic lines onto each membrane here. Obviously, for the sake of time, we're already running out of time. I have done that already with an already saved model. So we continue placing those geodesic lines, and then once we're complete with that, we just simply go up to Tools, Generate Cutting Patterns from Cells. It's as easy as that. Now, the program asks us which surfaces. We're going to select surfaces 1 through 5 here, which is automatically populated, and the program automatically detects these different cells to generate these cutting patterns. So what I'd like to point out is that our cutting patterns are now available to us in our project navigator. And you can see, again, they're synced up in the graphical view here as I go ahead and choose the different ones in my project navigator. We can double click on any one of these cutting patterns. And this is where I want to point out that we can go ahead and add in here what's called compensation, which we already covered, in which case we now have a compensation tab that we can add in a percentage in the warp and weft directions. We also can account for those allowances. So under the Allowances tab, this is that additional fabric. And in our case today, we want to add in some additional fabric for those welding seam lines of 0.16 feet. The border lines, let's say we want to add in 0.33 feet. So that's going to be applied to this particular cutting pattern. Now, if you don't want to apply it uniformly to all of the line elements for that pattern, you can choose the option here to define different lengths as well for each border line. So once I've done that, and by the way, you can select multiple cutting patterns here and apply the same allowances to multiple patterns at once rather than individually selecting them. So I would click calculate, and this takes, once again, just a minute to run. So we'll jump to an already saved model. And here we are once we generate those cutting patterns with our results available to us. So we can use our drop-down box to choose RF cutting pattern here. And what you'll first notice is that for each cutting pattern, what would initially be presented to us here is our table format. So you can see that as I begin to scroll down through this table, this gives me the X and Y coordinate points along the entire boundary lines of this particular cutting pattern 3. We can display here our allowances that we've added in, as well as the FE mesh here. So this is the information you could export directly to Microsoft Excel if you'd like. It's also available to us in our main RFEM tables. The statistics is pretty important to point out. The area of our 3D shape was 151.17 square feet. If we take a look at the area for the 2D shape, after that flattening process has been applied, we have 151.19 square feet. That's almost identical. We're off by 0.02 feet. So again, this just goes to show you that something like the minimum energy method has a very accurate process of flattening these 3D shapes into 2D surfaces, which we can give to our manufacturer. The other thing I want to point out is that we have results available to us during the flattening process just like we would with anything else. So we choose that option here in our drop-down box, and in particular, if we take a look at our strains, this might be important for determining what our compensation percentages should be. So we can view those strains here for our surfaces graphically within RFEM along with our strain values here. Again, everything is available to us in our tables. So I want to lastly show you guys how to export these files to AutoCAD as well as REVIT. So we'll start here with AutoCAD. I can go to File, Export, and I have a cutting pattern tab available to me here. This is where I just tell the program how many patterns I'd like to put in one row, the distance between the patterns, and I click OK. This is going to create a DXF file on your computer. What we can do with that DXF file is open it in AutoCAD. And what we will be presented with once we open up that DXF file is, first of all, if I can orient this correctly here, you will be presented with our 3D view of our membrane structure. So these are our fabric membranes. If I zoom in here very, very closely, I see a small number here. This number represents the cutting pattern. Now, of course, we can increase these numbers if we'd like to do so within AutoCAD. Well, if I scroll over to the 2D flattened patterns and I scroll all the way in, we should see a number available here. So that's nice that we can correspond these 2D flat elements to our 3D surfaces here. Now we can take this and do whatever we'd like with it in terms of printing it out for our manufacturer. So jumping back then to the RFEM model, what else we can do is to take a look here at one of our load cases. And we'll view only the first load combination here with a 1.6 live load applied. With this, I'm currently viewing the deflected shape, and we'll decrease the deformation factors, and we take a look at our structure here. What we can do with this information is export directly to AutoCAD. So the first thing I want to do is to make sure here that I have a new file open within AutoCAD, which I do. When I use this direct export to AutoCAD, the program first searches for an AutoCAD license. I want to check this option for the deformed shape. I want to set the units to inches. That's what I currently have set in my AutoCAD, and I click OK. Now this is different than creating a DXF file, but rather the program is going to automatically shoot that model into, which if we can open it up here, There we go. Sorry about that. Okay, so we can open it up here in that blank model, and you can see that the structure is automatically shown to us directly within AutoCAD. So that's just the difference here of a direct export versus creating a DXF file. This is my deflected shape of my membrane surfaces under that live load. So maybe perhaps we can change this to a shaded view here instead. Then under our layers, maybe we want to deactivate the initial form finding mesh shape that was found by the program, not under the live load, and then we can scroll all the way down to the bottom. Maybe we deactivate here the additional line elements. So now we're presented with a nice format for the deflected shape under that live load only of our structure. So what I can do with this now is go to File, Save As, and I want to save this as a DXF file. So I create my DXF file and I call this one Form Finding REVIT and DXF file extension. Save that to my computer. Well, now I'm going to jump to REVIT, and you can see here is my office building available to me directly within REVIT. If I'm interested in importing in this canopy structure into REVIT, I can do so with this option here called Link CAD. So program tells me I have to save my model, no problem, we'll get through that. And then we can select here our form finding REVIT file that we just created as a DXF. Now it's important to set here the origin to origin positioning. I click OK, and here is our canopy structure. Now what I do need to do is to select this object here, and we will move it to story 0, and it will shift it up. And now we can see that canopy structure available to us directly within REVIT to add to our drawings and so on. So quite powerful in terms of integrating with the different BIM options as well. So we can jump back to the PowerPoint here and go ahead and conclude today's webinar. As always, I know this is quite a bit of information. I also went over by a few minutes, but if you are interested in viewing more information on RFEM, these add-on modules, or anything else, you can find it on our website at dlubal.com. I also want to encourage everyone to follow us on our social media sites. In particular, I mentioned our YouTube channel that has all of our previously recorded webinars. You can also find information such as our newsletters, which events and conferences will be present at, knowledge-based articles, which are technical articles. If you have any questions about today's presentation or anything else, feel free to email us at our Philadelphia office at info-us@dlubal.com. Our phone number here is 267-702-2815. We will have many more upcoming webinars. You can always register at dlubal.com under support and learning webinars. As most of you know today, though, I typically send out an email notification about a week in advance of these scheduled webinars, which you can register through there. For PDH certificates, these will be automatically emailed to all participants today, so you don't need to individually request these. They will be sent to you within approximately the next 24 hours. Now, this is available for attendees that were here for the full presentation, and what I mean by that is a minimum of 60 minutes. So I take that into consideration. If you're only here for 20 minutes, let's say, and you don't get a PDH certificate, then you know why. Any additional attendees that were present watching under maybe a colleague's registration name and email, or you watched it as a group and you're also needing PDH, you will need to manually request those at info-us@dlubal.com. Again, info-us@dlubal.com for anybody who did not individually register for this webinar with their own name and email. And with that said, I want to thank everyone for attending today, and as always, we hope to see you at our next webinar. Thank you.